Today's lesson, we're going to learn how to figure out different types of chemical formulas. How do chemists come up with the chemical formulas that we've seen so many different times? And there's two types of formulas. One's called empirical and one's called molecular. So you'll need your periodic table, you'll need your calculator, and some paper to make sure you practice some problems along the way, because there's a lot of problem solving today. So first, let's make sure we know what the two different definitions are for empirical and molecular formula. Molecular formula is a formula you should be very familiar with. Those are the ones that we tend to work with all the time. This type of formula shows the exact number of atoms that make up a molecule if you're dealing with covalent compounds, or you're dealing with a formula unit, which we know are used for ionic compounds. The other definition that we need to be familiar with is empirical formula. Empirical formula should be new for you. Empirical formula is going to show you the lowest whole number ratio that you see between the different elements in a compound. So basically, it's the simplest or most reduced form of the chemical formula. So let's compare our examples with molecular and empirical to give you an idea. This first compound here, C6H12O6, is actually glucose. Here, this is the exact number of atoms that are in a glucose molecule. If we wanted to break this down by a ratio, it would say there are 6 carbons, 12 hydrogens, and 6 oxygens. That's what we see here. If we wanted to know what its empirical formula would be, down here is actually an example of its empirical formula. When we look at this ratio 6 to 12 to 6, this is one that can definitely be simplified or reduced. We can divide all numbers by 6. So if we did that, we would get this formula. It would be 1 carbon to 2 hydrogens to 1 oxygen. So when we look here, a molecular formula tells you the exact number. Down here, the empirical formula tells you the same ratios. There's twice as many hydrogens as there are to carbon or oxygen, but it doesn't tell you the exact number of each atom that we need in a molecule of glucose. The other option, what if you have an ionic compound? We know ionic compounds tend to already be in their most reduced form. So a ratio for the actual formula unit, the molecular formula for magnesium fluoride, would be 1 magnesium to 2 fluorines. Can you reduce that ratio any lower while maintaining it being whole numbers? No, we can't. It's already its most simplified form. So over here, when we go down and look at an empirical formula example, it's the same for magnesium fluoride, 1 to 2. Sometimes the molecular formula is already in its empirical formula case. It's already in its most reduced form. So there's times where these two, for example, they match. The molecular and empirical formula are the same. But then there's other times, like we just saw with the glucose, its molecular empirical formulas will not match. Same ratio, but not the same number of elements. A little bit more on this, if we take a look at a few more examples together. It's also possible for compounds with different molecular formulas to end up having the same empirical formula. So how would this work? Let's take a look here. First, we're going to look at benzene, and we're going to compare it to something called acetylene. Benzene's a molecular compound, 6 carbons, 6 hydrogens. It's a 6 to 6 ratio. Acetylene's molecular formula is 2 carbons to 2 hydrogens. They do not have the same number of atoms in their molecular formula. But what if we reduce their ratios? 6 and 6, its most simplified form is a 1-to-1 ratio. Acetylene, same thing. It's a 2 to 2 ratio. What happens when you reduce it? It can go down to 1 to 1. So different compounds can be different in their molecular formula, but in their empirical formula, not the same. So why do we care? Let's say you're analyzing a sample in the lab and you found out it had 50% one element and 50% of another. That means percentage-wise, you know the breakdown of the elements by mass, but you still don't know exactly what it is. So you could have the same outcome for percent composition for both of these particular compounds, but it wouldn't answer the question. So knowing that this is a factor is something that you'd have to consider if you're analyzing more samples down the line. So how do we actually come up with empirical formulas and molecular formulas? We're going to try a few different examples in the lesson today, but first we're going to start off with empirical formulas. So let's take a look at our first example. Okay, so here's problem 1. Problem 1 says find the empirical formula for a compound that's 81.9% carbon, 6.12% hydrogen, and 12.1% oxygen. In these questions, a lot of the data that you will get will often be approximated by experiments, so sometimes the total percentage will be pretty close to 100, but not exactly there. There are no masses at all given in this question. We need some masses. So the first thing that we're going to do is pick a mass. What mass do you choose? You can really choose anything that you want. Since you know the percentage of each element, you could change any percentage into a mass. But I always like to use a very easy number where we have to limit the number of calculations we have to do. Since we're dealing with percentage, we know the total has to equal to 100. So why not just make your sample 100 grams? That'll make it very easy to change from percentage of element to mass of element. So first thing you want to do is state your mass that you're using. So I'm going to say I'm assuming 100 grams. Once I've done that, then I can automatically take my percentages and convert them into masses. So carbon comes first. My mass of carbon is 81.9 grams. It was 81.9%. Now it's 81.9 grams. Next is hydrogen. If it's 6.12%, it's going to be 6.12 grams. And lastly, I've got my mass of oxygen. 12.1% is going to be 12.1 grams. Now, this gives me amounts in masses, but in a chemical formula, I need number of atoms. And what relates mass and number of atoms? It's the mole. So before we can actually get to the formula, we need to convert our masses into moles. So how do we do this here? We know how to do that. We learned that earlier on. We can find the number of moles using molar mass. So if I have 81.9 grams of carbon, I'm going to need to multiply it by the ratio of carbon's molar mass, 12.01 grams per mole. I want moles on the top and grams on the bottom. When I do that, I'm going to get 6.819. Don't need to write down all the digits, but a few extra decimal places in these questions is always better. I would recommend doing that. Then I'm going to keep doing this for all of my other elements here. Let's just fix this up here. So, mass of hydrogen, we want to find the mass, or sorry, the moles of hydrogen. So 6.12 grams. And we're going to do the same thing, divide by its molar mass, which is 1.01 grams per mole. And we should get 6.059 moles. And then one last time with oxygen, 12.1 grams. The mass, molar mass of one oxygen is 16 grams per mole. So we need to divide by 16. And when we do that, we get 0.075625. I've put in an extra 0 in there. Let's get rid of that. That looks better. Okay. So now we've got all of our numbers in a ratio with moles. This technically could be used to come up with our chemical formula, our molecular formula, or empirical formula, whichever formula we're trying to find. But at this point in a formula, we know we can't have decimal places with atoms. They're always rounded to whole numbers. So this is a ratio here that we need to convert to whole numbers. This step after this has nothing to do with chemistry, it's some math. How would we change these numbers from ones that are decimal places into ones with whole number? So our trick that we're going to do here is we're going to divide by the smallest number of moles. So out of these three, oxygen is the smallest. So I'm going to divide it by itself. And why we choose the smallest one is this will eliminate it and always turn it into a whole number first, 1. Then I'm going to divide the other numbers by the same value, 0.75625 moles. And then I'm going to do the same over here. We're not changing the ratio here, we're just trying to get them into whole numbers. So if we do something to one number, if we do the same thing to all of the other numbers, it doesn't change anything that's going on. So when you plug this in your calculator, and you might want to pause and try it just so you can see what happens when you do this for carbon and hydrogen. If you tried it out, when you check your number, you should see that you get pretty close to 9 here. So we can round it to 9. And over here with hydrogen, it's pretty close to 8. So now when we look at our numbers, we've got 9, 8, and 1. Those are whole numbers, and those are some good things that we can use in a formula. This is representing how many carbons we have. This is representing how many hydrogens we have. And this is representing how many oxygens we have. Now we have our most simplified ratio, or our empirical formula. So now we can write a concluding statement. Our empirical formula, and we can just shorten that to EF, is going to be carbon first, and there are 9 of them. Hydrogen next, there are 8 of them. And there's 1 oxygen. We don't usually put 1 in the formula, so we leave it just like that. So that's how we calculate empirical formula. Let's try out another problem. This one's just a little bit different, but not any harder. There's just an extra step that we have to do. So what I want you to do and try is see if you can get to the first couple of steps. Find how many grams of each element we have, convert them into moles, and then divide by the smallest number of moles. So you do that first, see what you come up with, and then I'll show you where things take a little bit of a twist here, things that are a little bit different. So pause the video and give those first few steps a try, and then when you're ready to check, unpause, and we'll start walking through some of the answer. All right, let's start checking. The first step that you want to do is assume that you have 100 grams. Again, just like before, since we're dealing with percentages, we've got carbon, we've got hydrogen, both equaling to 100. Use 100 grams. That way you can take those percentages and directly convert them into mass. A lot easier. Then, masses we know aren't good for atoms. We need moles. So just like the previous problem, find the number of moles by dividing by the molar mass. Divide by carbon's molar mass, divide by hydrogen's molar mass. Once you've done that, you should get these approximate numbers for your moles. Now, What we're going to do next is divide by the smallest number of moles, and you'll see this is where things change. So, the smallest out of the two is 6.803. So let's divide both by 6.803. When you do that, the first number should be a little bit more obvious. This is 1. When we look at the next number, though, you get a number that looks like this, approximately 2.66. Is that closer to a whole number? Not really. 2.66 is kind of in the middle of 2 and 3. We want to get a whole number. So how do we do that? We're just going to play around with some numbers a little bit more. And again, remember, this is just a ratio. We just want to make it into a whole number ratio. So we're going to play a little game. And the easiest is trial and error. What happens if I multiply this number by 1? Does it change anything? No, it would still be the same. So I'm not going to multiply by 1. What if I multiply this by 2? 2.66 times 2 would give me 5.32. That also doesn't work because that's not really close to a whole number. So let's try it again. What if I take this number and I multiply it by 3? If I multiply it by 3, I get 7.98. Is that pretty close to a whole number? I would say so. So that means I can approximate this at 8. But remember in math, whatever you do to one number, you've got to do to the other. So the other half of our ratio is this number 1 over here. Since I multiplied this side by 3, this side I also need to multiply by 3. So when I do that, the 1 is going to change into a 3. Now I've got two whole numbers. Now I have my empirical formula. So here I can say my empirical formula is made up of 3 carbons and 8 hydrogens, and that's my empirical formula. So this is part 1 of our lesson with all of the empirical formulas. In part 2, we're going to see how to figure out the molecular formulas.